Hello and welcome to helpyourmath.com. In this video we're going to look at some examples of graphing logarithmic functions. Before we get started on logarithmic functions, I just want to remind us about the fact that logarithmic functions are inverse functions of exponential functions. And just to talk about some things that we might play a key role here in making sense about exponential functions. Exponential functions are of the form f of x equals b to the x. They have a horizontal asymptote at y equals 0, or if there was something going on, it would be y equals k, if there was, a plus k here. But if it's a parent function, we won't have that. And we also have a critical point. We find the critical point for the parent function is 0, 1. And then if there's transformations, then it changes to h comma k plus 1. But what we want to keep in mind is with inverse functions, they are reflecting about that line y equals x, and the inverse of the exponential is the logarithmic, so the logarithmic would look something like this, where it reflects about that line. So that's what we want to keep in mind with these logarithmic functions. So the parent function f of x equals log base b of x will have a critical point not at 0, 1, remember it's the inverse, so we switch x and y, at 1, 0. For transformed functions, g of x, we would have a times log base b of x minus h plus k, where the critical point is located at h plus 1 comma k. So that's where that critical point is going to be. And remember, the critical point, that's not a real thing, that's just a me thing. It separates where the graph of the exponential kind of is flat versus where it like goes up, 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 up. And we will see that here too. So we'll see it kind of like flattens out and then it goes up, 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 up. Logarithmic functions have a vertical asymptote, so unlike exponentials that have a horizontal, logarithmic functions have a vertical asymptote, and it will be found by saying x equals h. So that's going to tell us where that vertical asymptote is. Since it's a vertical asymptote, nothing can get around the vertical asymptote. The entire graph will either be to the left of the vertical asymptote or to the right. And one more thing just to note about logarithmic functions, so they are a little bit weird, and what I suggest doing is looking at the base and writing down some of the key powers of that base. So if we're talking about base 2, if we have log base 2, the key things that we want to keep in mind are that we know the powers when it's like 1/8, we know 1/4, 1/2. 1 will always be the critical point, so we kind of ignore that one. 2, 4, 8, right? Those are the powers of 2. So when we're thinking about logarithmic functions, that's what we want to focus on. We want the argument to be 1/8 because then we know log base 2 of 1/8 is -3. We want the argument to be 4. So what I usually do is I'll take the argument and I'll say, okay, we need to figure out what x value is so that we end up getting 1/8, and then we'll solve for x, and that's going to help guide us with these logarithmic functions. We want to make sure we take our time with these because these are a little bit weird. All right, we're going to start with a parent function, f of x equals log base 2 of x. And with this parent function, so again, what we want to keep in mind is that this is representing a power of 2. So x is a power of 2. I'm going to say powers of 2. And as I mentioned, what are the powers of 2 we care about? Well, 1/8, 1/4, 1/2, 1, 2, 4, 8. If you want to do 16, I don't have that on the graph, but you could do 16. And the 1, when you figure this one out, this will be that critical point, which I just nicknamed C period, P period, just for my own ease. What also might be helpful is then just knowing which powers these are. So these are the powers. What's the exponent of 2 to get 1/8? That would be -3. What exponent of 2 gives me 1/4? -2. 1/2? -1. 1, 0, 2, 1, 4, 2, 8, 3. So this is going to play a critical role in helping us create a table of values. So I suggest doing this. So this is the powers, and then this is the exponent that produces that power, if that makes sense. All right, so in our first example, what we want to do, identify the vertical asymptote. So the vertical asymptote, I'm going to where am I going to write this over here? The vertical asymptote will be at x equals 0. And identify your critical point. So the critical point, again, that's when the argument is equal to 1, and the argument will equal 1 at 1, 0. And again, let's make sure this makes sense, because if I plug in 1 for x, this is log base 2 of 1. So this is saying 2 to what power gives me 1, and that would be 2 to the 0. All right, so let's go ahead and set up our graph. We have our vertical asymptote at x equals 0, and we have our critical point at 1, 0. To create the rest of the graph, we want to choose a few values in between the vertical asymptote and the critical point, and then we want to choose a few values to the right of the critical point. And again, we want to be very careful. We don't just want to use our standard, well, we can't even use -2, -1, because those won't produce any x values. Those are undefined here. So we have to choose numbers, and we really want to choose numbers so that the arguments are these powers that we just discussed. Since we don't have a transformation, we get to just use these powers. So I want to use 1/8, I want to use 1/4, I want to use 1/2. I don't think when I write this that you can read it over the orange, so I'm sorry about that. And then, so I want the argument to be 1/8. 2 to the 1/8 we said is -3. 2 to the, I'm sorry, not 2 to the 1/8. 2 to the -3rd is 1/8. So with this logarithm, we would say here, log base 2 of 1/8, where 1/8 is x, is equal to -3. If we have an argument of 1/4, that means we had -2. If we have an argument of 1/2, that means we have -1. That's just going back to the table that I originally created to kind of help guide me with this. Okay, so those are some values in between the vertical asymptote and the critical point. Now, what about to the right of the critical point? Well, again, we want to choose powers that we know how to evaluate. So that's when I would use 2, 4, and 8. And then 2 to what power gives me 2? That would be 1. 2 to what power gives me 4 would be 2. 2 to what power gives me 8? That would be 3. So when we go to graph this, 1/8 -3 is going to be down here. 1/4 -2 would be maybe right here. And 1/2 -1 is going to be right here. So we see as we get closer and closer and closer to that vertical asymptote, it's really hugging that vertical asymptote quickly. On the other side, we have 2, 1, 4, 2, and 8, 3 up here. So we want to connect with a nice smooth curve. We don't want to cross our vertical asymptote. And we can see that as the x values get bigger, we're getting further away from that vertical asymptote. So this is a graph of a logarithmic function. This is the parent function. Another example here, so now we have some transformations. We have the negative indicating that it's going to be reflected over some horizontal line. And we have a shift. We're moving everything to the left. So everything's picking up and moving left. So a few things I want to do to help get myself set up. Let's identify our vertical asymptote. So this time the vertical asymptote will be at x equals -3. And I want to identify the critical point. And the critical point, remember, it should be at 1, 0, but now it's moving 3 units to the left. So it's going to be at -2, 0. The 0 is just because there's nothing being added or subtracted to the logarithmic function. So far we haven't really seen that negative come into play, but don't worry, we will. All right, so let's get our graph set up. Vertical asymptote at -3 will be right here. And a critical point at -2 will be right here. Now, before we create a table of values, let's think about what arguments we want to have. And remember, the arguments are going to be the powers of 3. So just thinking about powers of 3. And then we want to think about what exponent produces those powers of 3. That's going to help us with our table. So powers of 3 would be 1/9, 1/3, 1, which we know is our critical point, 3, and 9. And then the next one would be 27. So our goal is, this is what we want the arguments to be. We want to create arguments that are these numbers because those are the powers of 3. And then just so that we know for future reference, so that I don't have to keep challenging my brain, this would be, so 3 to what power provides 1/9? That would be -2. 3 to what power produces 1/3? -1. 3 to what power produces 1? That's 0. And again, this is the critical point here. 3 to the 1 gives us 3, and 3 squared gives us 9. So once we create the arguments, we already know the y values associated with them. So that kind of helps. These are not the x values because we have that shift in the argument. So what we want to do is we're going to take each power and we're going to say, okay, I want the argument x plus 3 to equal each power. So I want x plus 3 to equal 1/9. This is going to tell me what the x value needs to be. What do I want to plug in? Well, here I want to plug in -2 and 8/9 because I would subtract 3 from both sides, and 1/9 minus 3 is -2 and 8/9. So that indicates that's what I want to plug in. I'm going to create my table right here. So we have x and f of x. So one thing I know I want to plug in is -2 and 8/9. Because when I do that, when I plug in 2 and 8/9, so I'm going to come over here, -2 and 8/9, we get negative log base 3 of -2 and 8/9 plus 3. Well, remember, we designed this so that this ends up equaling 1/9. Now we know log base 3 of 1/9, if we go back to our table, is -2, but there's still that negative in front, so we get -2, and we end up with 2. Because of the negative in front, we end up with 2. Okay, that might have been confusing. Let's try it again. Next, what do we want our argument to be? We want the argument to be 1/3. So we need to force x plus 3 to be 1/3. What x value do we need to plug in? X plus 3 needs to equal 1/3. So we would subtract 3 from both sides, and that would give us -2 and 2/3. So next we want to plug in -2 and 2/3. And hopefully this kind of makes sense, because we are looking to plug in numbers between the vertical asymptote x equals -3, not x equals 3, and the critical point -2, 0. And these two numbers are both in between -2 and -3. So this is great. This means we're doing something right. Okay, when we plug this into our function, f of -2 and 2/3, we get negative log base 3 of -2 and 2/3 plus 3. Well, this, remember, we forced this to be 1/3. 3 to the 1/3, 3 to what power gives us a third? -1. But there's already a negative in front, so it's -1, and we end up with 1. We can skip the critical point. We already identified our critical point. It was at -2, 0, so we're spared there. But 2 more. So next we want to force the argument to be 3. We need x plus 3 to equal 3. So what does x have to equal? X must be 0. So we're going to plug in 0 for x. And if we plug in 0, a nice y-intercept, we get negative log base 3 of 0 plus 3 is 3. Well, log base 3 is 3 to what power is 3? That would be 1, but there's the negative that was in front, so we end up with -1. Remember, this negative is going to throw everything. It's going to switch everything. So it makes sense that in this case, what we feel like should probably be positive is ends up getting negated in the end. It becomes negative. All right, one more. So lastly, we are looking for the argument to equal 9. So we want x plus 3 to equal 9. That means that x needs to equal 6. So our last x value is 6. And when we plug in 6, I'm running out of space, so we're going to pretend like it says f of 6 equals negative log base 3, and then here it will be 6 plus 3 is 9. Well, 3 to what power gives us 9? That's 2, and then we have to negate it because of the negative out in front, so we end up with -2. Now we want to graph these points. -2 and 8/9 is really, really close to -3, and that gives us 2 up here. So don't do that. So it's like right there. -2 and 2/3 would be really close to -3 also, but not as close. We have our critical point. These get a little bit nicer. 0, -1 is down here, and 6, -2 is down here. So this time as the x values get closer to that vertical asymptote, the outputs get really, really, really big. And then as we get further away, as the x values get bigger, the graph gets more and more negative because of that negation in front of the function. And this would be the graph of f of x equals negative log base 3 of x plus 3. One more example. Ooh, this one's going to be scary. It's going to be great. We're going to get through this. Okay, so we want to create a table of values and sketch the graph of f of x equals log base 1/3 of x minus 1 plus 2. Don't be intimidated by the fraction. Remember, 1/3, that's just the reciprocal of 3. So we want to think about, again, what I suggest doing. Well, before we get to that, let's identify the two things, the vertical asymptote. So the vertical asymptote is going to be located at x equals 1. And the critical point, remember, it should be at 1, 0. It's going to be moving to the right 1 unit because h is 1. So now it's going to be at 2, and then it should be at 0, but it's being raised up 2, so it's going to be 2, 2. Okay, so what I suggest doing before we start the table of values, because remember, we want the arguments, we want this x minus 1 to be powers of 1/3, so that way we can quickly identify, or we can quickly simplify without having to do anything weird. So let's look at the powers of 1/3, and then what exponent it takes to produce those powers of 1/3. So the powers of 1/3, we might use 1/9, 1/3, 1, 3, and 9 are all powers of 1/3. 1/9 is 1/3 squared. 1/3 is 1/3 to the 1. 1 is 1/3 to the 0. 3 is 1/3 to the -1. And 9 is 1/3 to the -2. That's what we want to keep in mind as we look at this graph. And what I want to do before we get started on the table of values is graph the vertical asymptote at 1 and the critical point at 2, 2. And so remember what we're looking for here. What we're going to be trying to do is we're going to try to pick values in between the vertical asymptote 1 and the x-coordinate of the critical point 2. And then we're going to look at some values that are bigger than 2. But we want to choose wisely. So as I set up my table, since we're not going to be over here, I'm just going to set it up right here. And we want to choose our values carefully, as I said. So first, we want the argument to be 1/9. Well, how do we get the argument to be 1/9? That means that x minus 1 needs to equal 1/9. We would add 1 to both sides, and we would get 1 and 1/9. So the first x value I want to use will be 1 and 1/9. When I plug in 1 and 1/9, this would give me log base 1/3 of 1 and 1/9 minus 1. 1 and 1/9 minus 1 will be 1/9 plus 2. And we just did this, and this is up in that table up there. That's why I did it. 1/3 to what power is 1/9? That's 2. And then 2 plus 2 is 4. Equals 4. So when we plug in 1 and 1/9, we get an output of 4. Okay, what's the next value we want the argument to equal? We want the argument to be 1/3 because we know what 1/3 to the how to get from 1/3 to what power gives us 1/3. There it is. So we're going to say x minus 1 equals 1/3. I would add 1 to both sides, and that would give me 1 and 1/3. So the next x value I want to plug in is 1 and 1/3. When I plug in 1 and 1/3, I get log base 1/3 of 1 and 1/3 minus 1, which is 1/3, plus 2. This is the identity. Remember, any base with the matching argument equals 1, and then 1 plus 2 is 3. So here we get 3. I don't know why I just moved my line up, but it did. Okay. So next, we don't have to worry about this one. This was the critical point, which we've already identified as 2, 2. So our next goal is we want an argument of 3, because we know if we have an argument of 3, what this will simplify to. So we need x minus 1 to equal 3, which means x needs to equal 4. So the next x value we're going to plug in is 4. When we plug in 4, we get log base 1/3 of 4 minus 1, which is 3, plus 2. Well, 1/3 raised to what power gives me 3? That's the -1 power. And -1 plus 2 is 1. Okay, and then last but not least, we want to have the argument be 9. So x minus 1 equals 9 means we need to plug in 10 for x. So lastly, we're going to plug in 10. Log base 1/3 of 10 minus 1 is 9 plus 2. So this is saying 1/3 raised to what power is 9? Well, we know because we wrote the table there. It's -2, and -2 plus 2 is 0. So if we were to plug in 10, the output would be 0. All right, we're ready to graph this. Hey, hold on, go back. I'm not done with you yet. It's gone. Oh, good, it's still there. Okay, what happened here? I think I pushed the button. Okay, great. Let's try this again. I'm not going to push buttons this time. 1 and 1/9, 4 would be up here. 1 and 1/3, 3, maybe right here. What do we have next? 4, 1, and then 10, 0. So it's going up, up, up as the x values get closer and closer and closer to 1, and then it gets more and more negative as the x values get bigger and bigger and bigger, which makes sense because raising 1/3 to bigger and bigger powers is getting really small. because the base is in between 0 and 1. It's like exponential or logarithmic decay, I guess. And this has been a video on graphing logarithmic functions.